Got involved in security in '83. And then ACoD, the congressional stuff was actually 91, but thank you for the 60-year differential. And then I wrote 3 volumes on how to conduct information warfare, which have been used by the United States, and the only other country in the world to actually license the book was China, oddly enough, and they've been following it. I also founded InfoWarCon, so I've been involved with information warfare a great deal over the years, and kind of got out of it because I got sick of the whole Beltway thing. What I do for money is I just sold my company doing security awareness training for corporations around the world, and now I finally get to come to these things and enjoy them. So I'm going to start it off with kind of 3 basic statements. Shit's broken. Fine. The next generation shit ain't going to fix it. And if I mention a vendor and insult it, fuck it, that's what I'm going to do. My job is to sit up here and present you with some ideas that are different. Hopefully they're different, things that you have not heard in your day-to-day thinking or the readings or all the pontifications that have gone at all of the various conferences. Your job is to call bullshit on me and do it Thank you! And you have to do it with a beer afterwards at the following event. So the Analogue Prism, a couple of fundamentals. Bullshit. No, they're not yet, not yet. Why is there no screen? Is that on me? Which is the button on this fucking thing to do this with? Oh, it's not plugged in. How about that? You didn't. That's HDMI, and I do not have an HDMI on this machine. Do you have a? Yeah, no, this is that super bullshitty Apple thing. All right, so I'll talk through the bulleted slides. You don't have to look at them. The security model, the basic way that we're protecting the planet these days is on a model that was established 44 years ago by Anderson in 1972, and it's called the reference monitor. And the vast majority of the technologies that we're using today in order to quote-unquote defend and protect, which I do not believe in at all, are still being used. Number 2, I'm hoping that the majority of you, in order so I can get through this quickly, understand massive amounts of electrical and fundamental engineering principles. I don't have time to go through all the basics and all the teachings. There we go, cool. Hopefully you can mentally get this stuff really fast. This is not a 101 primer. I'm assuming you are some of the smartest mofos around there. And I only got 30 minutes, but you're going to buy me beers later for this. The fundamental philosophy behind this model and concept of cybersecurity is to absolutely kill absolutism. We are living in the binary, digital is binary world, and I totally reject the concept entirely that digital means binary. And I can go through all the engineering reasons. For those of you with some background, you know what I'm talking about. I'm going to eliminate zeros and ones from all of my discussions. I do not believe in defense in depth, and I'm going to show you why I believe in detection in depth. And I'm going to use a little bit of math in this to be able to give you, hopefully, some of the background and a little bit of convincing, and we'll finish it over later with the bar, as to how to make these things actually work. I'm going to be introducing some concepts of feedback, negative, positive, and OODA loops. In the earlier talk, there was an allusion to OODA loops because OODA loops are about high-speed analysis in distinction to troop movements versus aerial combat, or in our case, cyber war. The other thing that I was really concerned about while working on these ideas, I wanted to be able to hopefully improve security with making no fundamental changes to the existing infrastructure. So with that, we're going to begin with the book I wrote in '98, Fundamental Math, and hopefully some of you are familiar with it. In order to have a network with any level of protection or defense, you have to have a detection and reaction network that is mathematically provably stronger than your defensive equipment. Any vendors in the room that would like to guarantee the performance of their security products? Do you know any vendors who will? What vendor will guarantee a security product? Okay, so we got a couple. This is great. Principle being, we want to be able to measure security. We need to have some metrics. We've talked about it throughout the day, and there's been a lot of allusions to some of the analogishness of approaching security. Ultimately, we have a metric that we can work with, and the final formula down there is bandwidth divided by file size, starts to give us a look at our risk exposure when we're living within the time domain. The time domain, of course, is another analog domain. So where do we begin? Feedback. Feedback has a triad. The electrical, the acoustical, and the mechanical systems. We're all quite used to them. But have we ever taken that approach seriously in the way that we look at coding, networking, or internetworking? The mechanical abstraction for this is represented on the right with positive feedback in a mechanical system, and then 100% negative feedback in the other, and then the mathematical abstraction is up top. Every single feedback system in the world uses this as the fundamental mechanism. When we look at SCADA, people forget we have this. PLCs are fundamentally feedback systems that are tied to some sort of mechanical or electromechanical or biological process that tells us what is going on in order to make minute adjustments along the way. Again, we do not have zeros. We do not have ones. There is no perfect security, and there is no total absence of security. Everything is somewhere in between 0 and 1. We live in a SCADA world more and more in IoT coming along. Just think of the cars that we're going to be driving or not driving, as the case may be. These are all SCADA-like feedback-intensive mechanisms. And this is where we get into, on the left, the largest single SCADA implementation in the world is called the Delta Works in Holland, which protects it from flooding from after the storm in 1953. On the right is a typical GE modern engine, detection and depth. 5,000 independent sensors looking at its performance every single second, generating between 1 and 4 terabytes of data per hour, per flight hour. This starts adding up. And again, we're not talking about any protection here. Not one of these is a protective device. All of them are detection and reaction performance processes that make the protection and defense actually work. UDA is another kind of feedback loop developed by the military, John Boyd, for high-speed aerial combat. Get inside of your enemy's decision cycle. The decision cycle is militarily what's, in my opinion, much more important than big data analysis, because big data has a probabilistic amount of veracity as to what may or may not be coming down the line. But when you are in actual combat, be it cyber combat, or in John Boyd's case, it was aerial combat, getting inside somebody else's decision cycle meant one thing only: do it faster. Do it faster. Time, again, being an automated, an analog function. The complexities of UDA, they can get very, very deep, but they are fundamentally about analog feedback processes based upon high-speed detection mechanisms and the decisions that are made around them. Now, we also have positive feedback. Learning is positive feedback. That's kind of cool. There are the mechanical feedback systems of bridges with resonance of winds. Bad type of positive feedback. Again, if there were sufficient detection mechanisms and reaction processes in place, a lot of those issues would start disappearing. Now, this is something that we all actually use today. When I initiate a process, and I'm with Bank of America for my mobile banking, it says, I'm going to move some money and I'm going to send it over. Oh, you Bank of America? Much better than Chase, I'll tell you. You initiate a process and it says, I'm going to move a whole mess of money to Gotti because he let me speak. Then it's going to say, you sure about that? Is this the phone number to text something for? And it texts you and it gives you X amount of time to do a response that must match. And that's what is out of band, time-based analog feedback. Very simple concept. Bank of America was the first one that I was aware of to actually do the implementation of it. And it is something that I'm very positive, feel very strongly about. What you will also notice about this, it is based upon the original Anderson 1972 reference model. monitor model. And it was adapted for out-of-band, time-based feedback. Now, my wife's car does this. She got one of those new Lexuses. And what does this say here? All it says is, we have an AND gate. And the AND gate in here, for that, hopefully everybody knows Boolean logic well, basically says, I want to make a turn. So that's one input to the AND gate. Now I want to verify that it's safe to turn. Second part of the AND gate. But you'll notice in the decision time, there's a clock, an analog piece of feedback that says, how much time do I actually have to make this decision and maintain safety? This is what autonomous cars are being based upon and what my wife's car does. And I turn off and I drive an old 6-speed manual from the 1920s, Gotti, and it's still good. Still rocks. Yeah, it's called a model fuck you. Yeah. So we're starting to do some of these feedback conditions, which is a human condition. We have been trying to get computers to adapt to computers versus getting computers and technology to adapt to the human condition, which means that we have to go analog in order to do it. So after several years of playing around with this stuff, came up with what I believe to be a very fundamental circuit. Everybody hopefully is familiar with RS flip-flop logics and how the inputs and outputs all work. So we'll take a simple Alice Bob here, and we're going to use this for the case of a banking transfer. We'll call it the two-man rule, where two people have to do and approve a process. Traditionally, it was Alice will do it, then Alice will send Bob the piece of paper to sign. Some amount of time has to occur in between that, or maybe Bob's out to lunch, maybe he's out of the, whatever. There was no time-based criteria, and the validation process and critical modes ceased to work. However, in this particular model, what we did is looked at Alice making a decision, have a Q output prime saying, yes, we will allow that to occur. However, based upon policy, Bob has to approve that decision within X amount of time, otherwise there's an automatic revocation of that process. Now, at the human level, that could be 2 minutes, 2 hours, 2 days. If we talk about trust and code, how fast do we want this to be? We're going to be 10 to the minus 6th, perhaps 10 to the minus 9th, depending upon the environment we're working in. The time scale is immaterial because fundamentally, when you look at analog security, it is fractal in nature. So it takes an entirely different view of networks, security, code, internetworking, because it's all fundamentally the same problem. And then we have continuously variable truth tables that come as a result of that as well. And these are analog truth tables that we had to develop independently because I couldn't find one back from George Boole's work. Now, trust, that word got brought up a lot of times today. Human trust, code trust. What is trust? Well, again, for me, trust has no zeros and no ones. It's somewhere in between. Now, how do you determine that? Well, maybe Bank of America, for their engineering department, has a set of criteria by which they're going to develop trust. Certainly the CIA had great trust in Aldrich Ames. The FBI had great trust in Robert Hansen. But what they didn't do is employ an analog feedback vetting process to have that periodic review to reevaluate what is that value of trust. And the value of trust becomes very, very important when we start looking at how to figure out the probabilistic, and I'm using Bayesian probabilities, nothing terribly fancy, to understand what happens, especially or initially in multi-user administrative functions. So hypothetically speaking, my trust value is 9, and his is, it's 0.9, because there's no such thing as a 1, and his is 0.9, based upon whatever HR policies say they're going to be. Using Bayesian probabilistics, because we're into an OR gate decision-making process, when we have multiple administrators on these networks, suddenly our overall trust value is now decremented down to 0.81. Trust factor then can be viewed as an inverse function of risk. Key concept here, they can be looked at as a 1 over x function depending upon how you're trying to view your network and what question you're trying to answer, and you're hopefully not looking for a 0 or a 1 in the process. So, do we trust our products? How do we measure our products? Well, let's say there are two competing antivirus, IDS, IPS, whatever. What I want to do is stack them up on a bench. No, I want you guys to do it. I want the lab guys, the guys that know how to do this shit better than me. Stack them up on a bench under identical operating conditions, optimize, let the vendor sit there, and what we have is two things, two inputs. We have a known good input, we have a known bad input. I, as a good engineer, should be able to drive the inputs of my black box, because I don't care what the detection mechanism is. It's immaterial what it is. It's a black box, known good input, known bad input. As soon as the known bad input is inserted, we start a clock, an analog function. How long does it take that particular detection device to be able to give you a high probability, which develops back into trust factor, output that stops the clock to give you a hardcore measurement? So does IDS product A take 1 millisecond and IDS product B take 4 seconds? I don't know the answer. We have the capability now to do this, to benchmark these by simply putting in a clock-based feedback network and calling the vendors out. How do you really perform? Put them up against each other and you're going to piss off an awful lot of vendors, and I want to see the videos, or I want to be there. Because it's kind of hard for me to imagine we've never done this. And all we're looking at is limit functions. We're looking at minimum, maximum, limit function. No, you're supposed to be taking pictures of me, dude. Come on, not that, me. And again, we're back to protective circuits and protective time having to be greater than detection and reaction time, and we're going to find a way to actually solve this. So this gives us another basis of a measurement of trust. We have the human trust level, technical trust level, which is the delta between the minimum and maximum performance levels of the equipment that you're measuring with. Again, no huge magic here. You've also got feed forward and feedback to keep in mind, because we're talking about in any system, whether it is a mechanical, acoustic, electrical, or a network, there is an introduction of noise, a disturbance. We tend to call that malware, ransomware, and all sorts of Ddos stuff. That's fine. From a systems engineering standpoint, it's the introduction of a disturbance. It's how we detect that disturbance and react to that disturbance. And that's exactly how neural networks are now modeling the brain, using feed-forward and feedback processes in order to learn. So whether we apply heuristics or neural networks to this, that's a question for the future and the big data guys, but the principle is the same. They are both analog functions. So now let's take it to the next level and say, I just don't care about the detection, and I think it was you, Sunil, who were mentioning reaction. All right, once you detected it, in the old days, in the 80s, there was a stack of paper. There's our logs. What the hell do we do? Well, nobody's going to have time to read them. Screw it. But now we're getting better reaction things going on. Can you measure the reaction? Reaction I call the triage, the actual taking care of the problem, and the final policy-driven remediation. How long does it take? If you do not know how long it takes within your organization to do this, you're doing something wrong, because the detection of the IDS vendor, that's all great and dandy. Now, are you using the same product to do the remediation? Maybe. Maybe it goes out of band into another product. Maybe it goes out of band into the human chain. All sorts of possibilities depending upon the policy and architecture of your organization. Measure it. You have the capability today to measure these things. And I don't know why we're not doing it. The term squeezing the loop, you'll notice here, is feedback, and this goes back to the OODA loop concept. How fast can I make this happen? How fast can I push the system till I push it over, and in old analog terms, we call it cracking the hysteresis loop, before the system itself collapses. And it's stressing the systems, because we're dealing with super high-speed stuff, and we kind of take it for granted. Yeah, it'll detect it, we'll fix it. How much, how fast Will that system work before it actually does collapse? Now let's add another element from my analog days, and it's called negative time. Anybody remember Led Zeppelin, Whole Lotta Love? And he's going, whoa, and have all that echo thing. That was done through a technique called negative time, and we used analog tape machines spread across the control room, and the other word for it is called a delay line. And we could adjust it mechanically in the old days before the digital circuits came up. Now, let's look at phishing, for example. There are certain companies out there that claim they can detect phishing. Well, that's great and dandy. If, however, we enter a delay line into the click-through process from any device, and the vendor who claims that they can detect any phishing thing within 1 millisecond, 1 second, 10 seconds, whatever the number is, let's prove it. Once that is proven, if I have my delay line put in here and I take the vendor's number and add some nominal constant C on top of it, what happens automatically? What? Anybody? Exactly. And therefore, the odds of a successful phishing attack go down by orders of magnitude, and there's a lot of math behind all of this. And all it is measurement of the vendor's products, using the benchmarks, introducing a delay line greater than the performance that's measured, and you end up with a negative time introduction, and we should be talking on the order of milliseconds here, a couple hundred milliseconds. Now, is that going to potentially degrade the performance for a user?
You forgot your coffee.
You mean my beer? Thank you, but screw the users. Seriously, what's more important, getting your network infected or having a user delayed by 200 milliseconds? What are the absolute numbers here? I don't know. This is the research that we're trying to get done. Now, let's take it to the next level and look at DDoS. So we got two different kinds of networks over here, and the one over on the right is the one that we tend to live with a lot more than we do today. Measuring DDoS products, same principle, introduce disturbance into the system, have measurements come out of it, compare products, and hopefully your DDoS vendors have some concept of time, and you're not going to find 2 or 3 orders of magnitude difference. I don't know the answer, but we should be able to find this out. The process is absolutely identical. Now, solving DDoS the way we're looking at it today is been relegated to the end user, the enterprise. Go fix it, and we'll do this little magic box here, and we'll do a magic box there. Well, let's look at it from a different standpoint. One of the gentlemen earlier was talking about protocols, and it just really struck home with me. And I don't have the slide up here because I was trying to keep this short. I have a black box detection mechanism inside my network at the enterprise level that says, this is funky traffic. Now we're trying to deal with it internally. So this is where detection and reaction come in. What if I had a protocol between machines that said source IP, destination IP, timing, and lots of other little kind of RFC kind of things that we want to have in there that'll allow one computer to tell another, this is what I'm seeing. Now we have to go back to out of band because so many of the DDoS attacks, actually overload the primary communication channel, and this goes back to the analog world I used to live in, was external control channels. When all else failed, the external control channels took charge. What if our detection and reaction, time-based out-of-band network communicated with ISPs? What suddenly starts to happen? We have a reaction matrix that's going to be policy-driven. So take a small isolated network, and in some cases, the answer is turn it off. Some cases, it's leave it on. But we have forgotten the concept of graceful degradation. Is it always necessary to have a binary answer? Or is there a performance issue somewhere in the middle that could be policy-based that says, wait a minute, I see something funky happening here. Let me maybe slow things down a little bit. Maybe just block a few ports. maybe just take a minor action to see if it resolves it before going for an all or nothing binary approach. So in a closed system, I introduce noise into the system. I have a detection reaction matrix module sitting at each of, we'll call them the perimeter router, for lack of any other word right now, and allow them to all communicate with each other over the detection reaction interface and protocol. So what happens? The enterprise, the guy's getting nailed, is the first one to notice it. Goes, shit, I'm getting nailed. Who do I tell? Well, I'm going to tell the detection reaction matrix. I'm seeing this. Well, the guy along the next hop is going to go, shit, I'm seeing that, and he says it's coming from me. I'm going to filter the hell out of that. Now, that's the next hop along the chain. This is the world we live in. We've got the tier ones, and they go all the way down to the little local ISPs. What if every one of the tier one, tier two major ISP feeds tied to a common detection reaction interface with a DR protocol that says, here's where the bad shit's coming from, please take care of it and go talk to the next guy because you know where it's coming from. And we end up, depending upon what our architecture is, possibility of having, what is it, a few hundred major ISPs around the world willing to communicate with each other with the same protocol. Real simple, real simple. And then we add in our delay lines because we don't want certain traffic to get through. So if we know how the performance of the detection system actually works, the entire enterprise and first hop to the ISP is based upon some nominal amount of delay. We take the performance of the device, add a constant time on top of it in order to mitigate any of the damage, and communicate it up to the next hop. Now, we also can add in the Alice and Bob situation with our flip-flop, our time-based flip-flop in there, because there's going to be varying conditions. Not everything is always going to occur within the same amount of time. So by entering in the time-based flip-flop in the middle, the Alice and Bob functions have an input from the source and an input from the output of the entire chain, and it gives us a comparison basis, time-based, that can be continuously adjusted in an OODA loop fashion. Ultimately, we're looking at something like this, taking this and extending this model across the entire internet. No modification to existing TCP/IP protocols, no change whatsoever. These are module and appliance add-ons, completely out of band, typically fairly low bandwidth communication along the detection reaction interface. And what happens to DDoS? What'd you say? DDoS is dead. What happens to spam? And we have an identifying last hop. We'll be able to get back to the source better than we ever had before, with not ever having to even bother with traditional trace routing along the primary communication channels. Again, that's something we know does not work. What else can we do with this approach? I've been playing around with ideas, and yes, crash pitch, I got a book coming out on this. Quantification of risk, taking trust factors at the code level, at the network or internetworking level. We have all the charts and all the math and the formulas, and we're giving them all away for free. Distributed attackers, multi-user administration. Typically, in many organizations, you've got 6 to 7 people with the same credentials for running mission-critical components. When you run your Bayesian analysis on it, your trust factor has gone down between 40 and 70%. This is a meaningful number to the people who are handling your risk analysis. Time-based authentication, yes. Bullshit. Thank you. I appreciate it. Well, that's the first beer for later. Revetting, building this into code. Imagine if we build this into code from the very, very beginning, where you have a feedback-based vetting process that does not use absolute trust the way that we do it today. Time-based metamorphic networking. It's an obfuscation technique that has been discussed. If it is done on a time-based mechanism tying into the DRI, suddenly new answers start appearing. And this is what I've discovered playing this and thinking about this for several years. Any question you ever have about security, must include the word time. Any answer that you have when it comes to security must have time. Otherwise, we will continue to live in the static world we live in today that we know damn well does not work. So what can you do today? You do today when you go home. Measure the detection systems in your network. Just your own, not even compare them. Get the vendors, SC Labs or whoever does all that stuff. Get them to start comparing the performance of these with a common metric that works for security, risk, and privacy. Measure your own detection processes. You can do this now if you sit down and write a few lines of code. Measure your own reaction. Measure how this triage, what is your performance there, and it works across all domains. I know my time is up, and I tried to get a lot of shit in there really, really fast, and I'm here to talk for the evening. If anybody wants to either one call bullshit on me, Gotti, or let's get into it and really see if there's something here that may be applicable for everybody across the planet. Thank you very much for your time. I appreciate it. Any questions? Oh, good. All right, I'm done.